Okay, I think now you're ready, yes?
Yep.
Okay, we are all ears.
Oh, okay. So this is a magnetic acceleration platform, or MAP, that I have developed for my Year 12 research project. I was inspired in building this from a whole series of science fiction novels and movies. Magnetic acceleration is a popular idea in science fiction, and it's becoming a reality at the moment in both military and travel. The method I've gone about building it is I first had to decide what type of magnetic acceleration platform I was building, because there are several types. There's a rail gun and coil gun variety. And in this circumstance, I chose the coil gun variety as it is a much simpler and easier method for someone with my kind of budget. The coil gun works by a series of electromagnetic coils. You pass electricity through any one of them, and it generates a magnetic field that varies depending on the current and voltage that is passed through. So it generates a constant magnetic field through the center. There's a hole in the middle where this tube runs through, and a nail or piece of metal which I've got placed inside the tube will be attracted towards the center of the coil. And the idea is to turn off the coil just after it reaches the center, because if it passes the center, the coil will start to bring the projectile backwards. Unfortunately, I cannot get my microcontroller to work, so firing backwards is almost a certainty. But I can do a short demonstration now and see if it works.
So before you do the demonstration, you have to explain that you try two ways. One is the manual, and the other one is?
Using a microcontroller to time it, so using a whole variety of electronics. I'll start with the manual method. So with the manual method, I'm just getting a wire and touching it to a battery, or in this case a power supply, which I've got here. The power supply is capable of supplying 40 amps, which for a coil should generate roughly 1 Tesla of magnetic force. It's difficult to explain exactly what a Tesla is, so I won't go too far into it. But your average household fridge magnet is about 0.05 Tesla, so it's a very strong magnetic field. So I'll demonstrate.
And for those who don't understand, this magnetic field is created by your?
By the coils.
And that's why you have so many there.
Yes. So I can only do one at a time with the manual method. So I'll be using this one here. The microcontroller uses a series of little chips that act as electronic switches. So if I apply power to one of these pins, I think it's the outer pin on this side, it will allow current to flow from this heavy section here through to this outer pin on this side, which I've wired up here. I've got an example here. So I would apply the current from the power source to the top pin here, and this it would be in the off state right now. If I apply a little bit of power to this here, it will activate it and allow current to pass through this and out this wire. And this wire leads to a coil. So that allows me to use a electronic switch, basically, which will be controlled by a microcontroller. The microcontroller is a BeagleBone Black. It's based on the Raspberry Pi, but it has been made by Texas Instruments. It's reasonably new, came out a couple of months ago, so there's not a lot of documentation on it. So I had to do a lot of experimenting with it in order to get it to work.
But you need to use your electronics program.
Yes.
Who has created it?
The program that it uses is a open source program called Cloud9, developed by a whole series of developers. It allows you to program in multiple computer languages and store them on the internet for retrieval anywhere you can connect to the internet. In this case here, I am using a mixture of JavaScript and a proprietary software based on JavaScript made specifically for the BeagleBone hardware.
Who wrote? You did.
Oh, yes, I wrote.
You have to explain that to people.
Yeah.
You are giving the instructions
Yes.
with your programming
Yeah.
to the microcontroller to suit. Yes?
So I've written a program on which you can see here. It has 108 lines of code. So here I've defined the pins that I have connected the switches to as a whole series of output pins, which I'll show you now. So I would wire, so these are all input and output pins, so called I/O pins. I would connect the little wire on this one here. I would connect to one of these pins, and using this chart, which is available on the internet, to tell me which pin number it is. I then put that pin number into this program. So, for example, I've got P810 here. So that tells me that I have selected, so P8, this is P8 and P9 rows, well, terminal blocks. This one is P8, and the 10 tells me that it is the 10th pin. So it goes 1, 2, 3, 4, 5, 6, and so on. So I know that the 10th pin is on the outer part of the terminal block, and I would connect it there, run the program, and this would send a small electrical current through that wire to activate the switch and hence activate the coil. Unfortunately, the microcontroller has a very low output voltage and is not high enough to activate these pins, these switches. However, these switches are the only ones capable of doing the full 40 amps provided by the power supply here. So I had to get another set of switches called these are transistors, by the way, to allow me to fire from activate the first set of switches. So I have to have a switch to activate a switch, which is proving very bothersome at the moment, as it's still not working. And if you look at the display here, I can actually activate the switches simply by touching them sometimes. There we go. Which I cannot explain, and I've asked an electrical engineer his opinion on this. He also has no explanation as to why it works when you simply touch it. It shouldn't be happening. So I've been having a lot of trouble with that lately, and at the moment that's the bit that I will have to overcome next in order to get the microcontroller to work. So I will, so that's the microcontroller side of things.
So that's a challenge you have to overcome. At the moment, though, your contraption works manually.
Yes, at the moment it only works manually, which means I can only fire one coil. In this case I'll be firing the first coil because the magnetic field only extends a couple of centimeters either side, so using any of these coils, it will not work with the nail placed where it currently is. So the reason I can only do one at a time is because once this one is activated, it passes through all of these in a few hundredths of a second. And human timing, I cannot by hand accurately time it with that kind of accuracy. The other problem with firing manually, also to do with the inability of human accuracy. If I leave on too long, it will shoot backwards, which is, you're most certainly going to see that unless we're very lucky. That happens probably 8 times out of 10. So I'll attempt to show you that now.
So let's show to our audience what you have constructed there. And you have to explain how it was made first. You have to explain that you measured the distances. Come on, tell us something about this.
Okay. So initially it was just going to be this center tube here, and it was all going to be entirely waterproof. That was so that I could perform a test underwater to observe the effects of a different viscosity fluid on the motion of the projectile, in this case the nail, rather than traveling through air. Unfortunately, that proved that wouldn't be a worthwhile endeavor at this time. So for the moment, at the time I decided I would redirect it so it just fires in air. This made the design a little bit simpler. So I already bought this central rail and I had to make the coils by hand. So I bought a big 1.5 pound, which is almost 1 kilogram spool of copper wire. And I got a drill motor to spin a central point, and I would wrap the wire around it a little bit and start spinning, and it would draw off the spool and it would coil itself up quite nicely. It's definitely not, you can tell it's been made by hand by how rough it is. It's not very compact. You can separate them quite easily. I would have bought them individually, but they're quite expensive if you buy them individually. So this spool cost me a total, if you include shipping, about $40. If I had bought each coil... So
you do have limited, we know.
Yes.
Limited means it's out-of-pocket expenses. That's a challenge for you. It's not scientific.
Yes, I had to buy
lab.
these myself. If I had bought the coils individually, they would have been... probably could have been easily $100 if I done them individually by themselves. So I saved about $60 by doing that. So I made that was that originally. Then the problem of powering the coils arose, and I got the idea from. So in a computer, there are what are called 12-volt rails. They're not actually rails, but I decided that given that I have this, I would make an actual rail for the current, for the power to pass through. So this rail on this side is the positive rail. When it's hooked up, it's set at 16.3 volts. I can change that if I want to, but having it at the higher voltage does increase the magnetic field produced. So that goes through, that's a positive rail. If I touch that, it's perfectly safe because of the very low voltage. It's not dangerous. Potentially you could lick it if you wanted to, and it would be just like a 9-volt battery. It would hurt, but it shouldn't cause any damage at all. And I've got a negative rail, which connects to the negative wire, so the power goes from here through the coil, and then through the switch that I showed you, and then into the negative rail here. on this side.
And all this soldering is...
Yes, it's all very rough soldering. This one is particularly, this one had to be modified because I actually accidentally damaged the switch by passing too much current through it, which is where I got this one from. I actually had to cut it out and replace it with a new one, which is why I have this one here. Because if you leave these switches on for extended periods of more than about 1 second, because I'm passing power through them, so you can think of this can output 800 watts. So if you think about your 800 watt heater in your house, you could have an 800 watt heater, that's about standard. Heat up your entire room in a few minutes. So you have an entire big 800 watt heater in a tiny little chip. So the heat builds up very quickly, and you start getting a little bit of smoke, and they melt, and then they stop working.
So excellent. That proves the magnetic field you're creating with.
Yes, that does prove that it had been working. So after having done the whole rail system, I had to have a frame to put it all in. So I used some MDF, which we have in our workshop at home. Used just some offcuts that we had lying around from my dad, who does his own projects. So I just got some offcuts of that, chopped it into little pieces, did some measurements, and drilled some holes for the rails to pass through these sections, and then glued and nailed each piece here on, threaded the rods through, and then soldered everything in place.
So I noticed earlier you said that you started with 4, but then you had to add one more coil or one more compartment, or?
No, not quite. I had to, so I made these 4, they were meant to be 5.
Okay.
But I forgot to make the 5th and had already laid out spaced like this. There's actually meant to be 2 coils per section, but because I mistakenly forgot to make one, I've had to put these 2 coils here. That's
an excellent way to overcome a challenge.
Yes, so that was the best way I could do it. So the exact spacing doesn't have to be a particular spacing, but you do want them to be a reasonable distance apart. Otherwise, the magnetic fields start interfering with each other, and then it gets very complicated with the physics, and things can break. Because when you have a magnetic field next to metal that isn't, so just use this as metal, and this one's turned on as a magnetic field. If they're too close to each other, the magnetic field from here can induce an electrical current in this one in the reverse direction of a similar current that's going through this one, and that would go backwards and could potentially damage or destroy my power supply.
Excellent. So you did manage to overcome another challenge this way. Great.
So I was very careful with that because it's not a cheap power supply, and I do not wish to have to replace it. One problem I did have with a different project, not with this one, is that a similar thing did happen, and the current went backwards and into my microcontroller and actually destroyed the microcontroller, which was not very good. I was quite upset about that one. So to ensure that didn't happen in this circumstance, to be absolutely certain, I put in a whole series, absolute ton, went overkill with this, of diodes, which only allow current to go in one direction, so it cannot go backwards. So I was worried about putting a lot of them in and going overkill. It was only a couple of cents each, and I have several hundred of them lying around at home because they're very useful in electronics projects.
So now we know that this has been constructed, how this has been constructed.
Yeah.
need to fire and see if it works.
Yeah.
Okay.
So, as I mentioned, it does accidentally fire just when touching it, and so I have to figure out why it's doing that. But I did that also I was explaining things to you, and the coil partially fired the nail to somewhere inside the tube. So if it doesn't come out of the tube, I have to lift it up as I have just done to get it to slide back to the starting position over here.
So can we show how we have set it up? We have set up your power pack. Can you show the power? Yes?
So this, I'll put this one off to the side. This power pack is necessary if I was going to be using this, which I won't be doing this time because